November 16th, 1942, Vancouver, Washington. The SS Joseph N. Teal slides into the Columbia River 71 hours and 40 minutes after her keel was laid. A cargo vessel, 455 feet long, constructed faster than most people plan a weekend. The previous record, 10 days. Traditional shipbuilding, 230 days, nearly 8 months. Henry J. Kaiser, dam builder, road contractor, never commanded a shipyard before 1940. Naval architects consider his methods dangerous. Traditional shipbuilders warn his welded hulls will crack apart in open ocean. But Kaiser sees what they refuse to acknowledge. America's survival demands building merchant ships faster than German U-boats can sink them. By November 1942, Nazi submarines are destroying Allied cargo vessels at a rate that defies replacement through conventional methods. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. For 2,000 years, ships were constructed the same way. Keel first, frames next, hull. Plates riveted one by one in a methodical climb toward completion. Riveting required 6 months of training to achieve competence. Kaiser's radical vision, welding could be taught in 10 days. One welder could accomplish the work of 2 riveting teams. His shipyards hired the unthinkable: women, wounded veterans, disabled workers, and African Americans barred from skilled trades by decades of discrimination. The Navy's Bureau of Ships issues dire warnings. Kaiser's welding techniques are unproven, catastrophic. Ship steel wasn't designed to be welded. Brittle fracture could split hulls completely in half. Lives will be lost. The established shipbuilding industry watches with alarm masked as professional concern. But Kaiser had proven one thing already. His SS, Robert E. Peary, assembled in Richmond, California in 4 days, 15 hours, and 29 minutes. That Liberty ship shattered every assumption about what industrial production could achieve under wartime pressure. The question wasn't whether Kaiser's methods were safe by peacetime standards. The question was whether America could win the war without them. The telegram that arrived at the Navy Department that morning in late 1942 contained production statistics that seemed to violate physical laws. 3 Liberty ships launched daily across America's shipyards. 18 merchant vessels per week. 78 cargo ships per month. Admiral Emory Land, chairman of the United States Maritime Commission, studied the numbers with satisfaction tempered by knowledge that German U-boats still maintained their killing pace. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. In June 1942, Nazi submarines were sinking Allied cargo ships at a rate that exceeded all replacement capacity using traditional construction methods. Britain faced starvation as Atlantic convoys disappeared beneath North Atlantic waves. America needed to transport 2 million troops and their supplies across 2 oceans simultaneously. At conventional shipbuilding rates, the war would end in Axis victory before sufficient merchant fleet capacity could be developed. Henry Kaiser stood in the muddy grounds of Richmond Shipyard No. 1 in December 1940, watching Todd Shipyard's traditional craftsmen assemble vessels using methods unchanged since ancient Phoenicia. Workers swarmed over skeletal hulls, each riveting team driving heated pins through overlapping steel plates with pneumatic hammers. 6 men per team: heater, catcher, bucker, riveter, each requiring 6 months of apprenticeship to achieve minimal competence. The hull would take 8 months to complete under optimal conditions. Kaiser's engineering background came not from maritime tradition, but from massive infrastructure projects that demanded revolutionary thinking. Hoover Dam, the Bonneville Dam, Grand Coulee Dam, projects where traditional methods meant failure and innovation meant completion ahead of schedule. Now, he faced a challenge that dwarfed even those achievements. Build thousands of cargo ships using a workforce that didn't exist, with construction techniques considered dangerous by every maritime expert in America. Kaiser's revolution began with a simple observation that shipbuilding traditionalists found heretical. Ships weren't monuments to be crafted by master artisans. They were products to be manufactured using assembly line principles proven in automotive production. Instead of thinking vertically from keel upward, Kaiser envisioned horizontal production, massive prefabricated sections built simultaneously in factories across America, then transported by rail for final assembly. The bow section could be welded in Pennsylvania while engine mounts arrived from Detroit and superstructure components rolled in from Seattle. Each piece tagged with numbers, corresponding to precise positions in the final vessel. Traditional shipbuilders called this concept impossible, impractical, dangerous. Kaiser called it the only way to build sufficient tonnage before Britain starved. The welding gamble represented Kaiser's most audacious break with maritime tradition. For 2 millennia, ships had been riveted. Steel plates overlapped and joined by headed pins hammered through both surfaces, creating thousands of potential leak points. The process was labor-intensive, requiring teams of skilled workers trained through lengthy apprenticeships. Welding fused metal directly, creating continuous seams theoretically stronger than the plates themselves. More importantly, welders could be trained in 10 days versus 6 months for riveters. One welder could accomplish the work of 2 riveting teams. The mathematics were undeniable, but mathematics had never sailed through a winter North Atlantic storm. The human element of Kaiser's revolution proved as radical as his technical innovations. With men being drafted faster than shipyards could replace them, Kaiser hired the previously unemployable, women who had never held industrial tools, wounded veterans missing limbs, disabled workers dismissed by other employers as incapable of precision manufacturing, African Americans barred from skilled trades by union prejudice and systematic racism. The shipyards became accidental laboratories of American capability, where performance mattered more than pedigree and urgency, eliminated the luxury of discrimination. Each worker learned one specific task, achieving precision through repetition rather than years of comprehensive training. Rose Will Monroe, working the assembly line at Kaiser's Willow Run bomber plant, reportedly inspired the iconic Rosie the Riveter image that symbolized America's industrial mobilization. Though in Kaiser's shipyards, the reality was Wendy the welder, women who fused steel seams with torches burning at 2,000 degrees Fahrenheit. The established shipbuilding industry watched Kaiser's early successes with growing alarm. These weren't merely business competitors, but threats to maritime expertise accumulated over millennia. Their warnings about welded construction carried the weight of centuries of accumulated knowledge. Riveted joints had built every great navy in history. When plates cracked, riveted construction contained the damage. Cracks stopped at joints between overlapping sections, prevented from propagating through the entire hull. Welded hulls created continuous metal surfaces where fractures could race unimpeded from bow to stern, splitting vessels completely in half. The steel itself hadn't been designed for welding. Chemistry developed for riveted construction might behave unpredictably when fused at temperatures exceeding 2,000 degrees. Kaiser was conducting the largest metallurgical experiment in maritime history, using vessels that would carry American lives through submarine-infested waters. By early 1943, Kaiser had reduced construction time from the industry standard of 640,000 labor hours to 352,000 hours per ship. His average completion time had dropped to 70 days, then 50, then an almost unbelievable 39 days. The Joseph N. Teal in Vancouver had stunned observers by launching after just 10 days of assembly. But these speed records represented more than publicity stunts. They were mathematical proof that American industrial capacity could outproduce enemy destruction when necessity eliminated conventional thinking. The implications stretched far beyond individual ships. German U-boats were sinking Allied vessels at a rate approaching 800,000 tons monthly. Britain's lifeline across the Atlantic was severing cargo by cargo. At conventional production rates, the Allied merchant marine would cease to exist before America could mobilize. Sufficient troop transport capacity. Kaiser's assembly line approach offered the only solution to an existential equation: build ships faster than enemies could sink them, or watch democracy drown in the North Atlantic. The production acceleration achieved by modular construction and welding assembly bordered on supernatural achievement. Where traditional yards completed perhaps 4 ships annually, Kaiser's facilities were launching vessels weekly by summer 1943. The prefabrication network spanning the continent meant that multiple ships could be under construction simultaneously, bow sections being formed in Pennsylvania, while engine mounts were machined in Michigan and superstructures took shape in Washington. When components converged at final assembly points, construction became a matter of precisely choreographed connection rather than laborious fabrication from raw materials. The ancient Phoenicians would have recognized the scene at traditional Atlantic coast shipyards in early 1942. Workers swarmed over skeletal hulls, each riveting team hammering steel plates one by one in methodical construction that had defined maritime manufacturing for 2,000 years. The rhythmic percussion of pneumatic hammers echoed across harbours as riveters drove heated pins through overlapping steel plates, then flattened the protruding ends with practiced precision. 6 men per team, each requiring 6 months of training to achieve competence. The hull would take 8 months to complete, assuming no delays for weather, material shortages, or the inevitable injuries that plagued industrial construction. 3,000 miles west, Kaiser's Richmond shipyards operated under entirely different principles. Instead of thinking vertically from keel upward, Kaiser had reimagined ship construction horizontally. Massive prefabricated sections built simultaneously in factories across America, then transported by rail for final assembly. The bow section arrived from a steel mill in Pennsylvania. Engine mounts were fabricated in Detroit using automotive assembly techniques. Superstructure components rolled off production lines in Seattle, each piece tagged with numbers that corresponded to precise positions in the final vessel. The approach violated every sacred tradition of maritime construction, which was exactly why it worked. Kaiser's most radical innovation wasn't organizational, but metallurgical. Welding had existed for decades as a repair technique used sparingly to patch damaged plates or seal minor leaks. But Kaiser proposed fusing entire hulls with continuous welded seams, eliminating the overlapping plates and thousands of rivets that traditional construction required. The implications were staggering. Welded ships used significantly less steel because plates didn't need to overlap. They moved faster through water because rivet heads no longer projected into the flow, creating drag. Most importantly, welding could be taught in 10 days versus 6 months for riveting, and one skilled welder could accomplish the work previously requiring 2 complete riveting teams. The human mathematics of Kaiser's revolution proved as compelling as the technical advantages. Traditional shipbuilding demanded armies of skilled craftsmen trained through years of apprenticeship, exactly the demographic being drafted into military service faster than yards could replace them. Kaiser's modular approach required workers to master single repetitive tasks rather than comprehensive maritime expertise. A housewife from Oklahoma could learn to weld superstructure joints in a week. A wounded veteran missing his left arm could operate overhead cranes with mechanical precision. Disabled workers, dismissed by other employers, found meaningful roles in Kaiser's assembly lines, their supposed limitations irrelevant when jobs were designed around human capabilities rather than traditional assumptions. The workforce transformation at Richmond Shipyard defied every convention of American industrial employment. Women comprised 30% of Kaiser's workers by early 1943, many experiencing steady wages and industrial responsibility for the first time in their lives. African Americans found skilled positions previously barred by Union prejudice, their welding torches burning as bright as anyone's. Veterans missing limbs, immigrants speaking broken English, teenagers too young for military service. Kaiser's yards became accidental laboratories of democratic capability, where performance mattered more than pedigree or appearance. The technical precision of modular construction demanded revolutionary thinking about standardization and quality control. Each Liberty ship contained exactly 250,000 individual components. From massive engine blocks to tiny electrical fittings, every part had to mate perfectly with its designated partner, regardless of which factory it had produced it or which coast it had travelled from. Kaiser implemented automotive-style tolerances and inspection procedures, creating the first truly interchangeable ships in maritime history. A rudder manufactured in Baltimore would fit perfectly on a hull assembled in California. Engine parts from Detroit were guaranteed compatible with transmissions from Chicago. The standardization meant Liberty ships could be repaired at any Allied port using components manufactured anywhere in America. The welding revolution required completely rethinking steel chemistry and thermal properties. Riveted construction had hidden fundamental flaws in ship steel for centuries. Plates joined mechanically rather than metallurgically, with overlapping sections that contained cracks at joint boundaries. Welding exposed steel to temperatures exceeding 2000 degrees Fahrenheit, fundamentally altering molecular structure in ways that maritime engineers barely understood. The fused seams created continuous metal surfaces where stress could distribute more evenly, but also where cracks could propagate unimpeded if the base material proved inadequate. Kaiser was betting America's merchant marine on metallurgy that shipbuilders had never tested at scale. Quality control in Kaiser's yards resembled automotive production more than traditional shipbuilding. Each welded seam underwent inspection to detect internal flaws invisible to surface examination. Workers rotated between stations to prevent fatigue-induced errors. Prefabricated sections arrived with detailed inspection certificates, documenting every dimension and material property. The systematic approach eliminated the craftsmanship variables that made traditional ships unique and potentially flawed. Every Liberty ship would be essentially identical, built to specifications so precise that components were interchangeable between vessels. The production acceleration achieved by modular construction and welding assembly bordered on the supernatural. Where traditional yards completed perhaps 4 ships annually, Kaiser's Richmond facility was launching vessels weekly by summer 1943. The prefabrication network spanning the continent meant that multiple ships could be under construction simultaneously, bow sections being formed in Pennsylvania, while engine mounts were machined in Michigan and superstructures took shape in Washington. When components converged at final assembly points, construction became a matter of precisely choreographed connection, rather than laborious fabrication from raw materials. The established shipbuilding industry watched Kaiser's revolution with growing horror masked as professional skepticism. These weren't merely faster construction methods, but fundamental challenges to maritime expertise accumulated over millennia. Welded seams had never been tested in North Atlantic storms. Modular construction eliminated the subtle adjustments that master shipwrights made during traditional assembly. The workforce lacked generational knowledge about how ships behaved in heavy seas. Kaiser was conducting the largest metallurgical experiment in history, using vessels that would carry American lives across submarine-infested oceans. And nobody really knew whether welded hulls would hold together when it mattered most. The competition between Kaiser's shipyards became a spectacle that drew reporters from across America by spring 1943. Richmond Shipyard No. 3 had shattered its own record so frequently that construction times seemed to exist in freefall, each launch ceremony celebrating achievements that would have been impossible the previous month. The first Liberty ship had required 124 days from keel laying to launch. By summer, Kaiser's average had dropped to 39 days. Then, Oregon Shipbuilding Corporation in Portland completed the Joseph N. Teal in 10 days, a feat so extraordinary that Navy inspectors initially refused to believe the documentation. Kaiser's response was characteristically audacious. He would build a ship faster than most people could plan a vacation. The SS Robert E. Peary became Kaiser's ultimate proof of concept, a vessel whose construction timeline challenged the fundamental laws of industrial manufacturing. Assembly began on Sunday, November 8, 1942, with prefabricated sections converging on Richmond from across the continent. The bow section had been welded in Pennsylvania. Engine mounts arrived from Detroit on specially designed railroad cars. Superstructure components rolled into the yard from Seattle, each piece tagged with numbers corresponding to precise positions in the final vessel. By Thursday evening, November 12th, the completed ship was sliding down the ways into San Francisco Bay, 4 days, 15 hours, and 29 minutes after the first keel plate had been positioned. The achievement represented more than speed. It was industrial choreography executed with precision that bordered on the supernatural. The production miracle, unfolding across Kaiser's 7 shipyards, defied every assumption about manufacturing capacity and human capability. By 1944, Kaiser and his competitors were launching 3 Liberty ships daily, more vessels than the entire American maritime industry had produced annually during peacetime. The scale was staggering. Nearly 1,500 vessels rolling down Kaiser's ways alone, representing 27% of all U.S. Maritime Commission construction during the war. Each ship carried the industrial DNA of a continent: steel from Pennsylvania, engines from Michigan, electronics from Massachusetts, lumber from Oregon, assembled by workers who 18 months earlier had never seen a welding torch or operated a crane. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Richmond transformed from a sleepy Northern California town into a bustling industrial metropolis almost overnight. Population exploded from 20,000 to over 100,000 as workers flooded in from across America, drawn by wages higher than anything available in their home states. Kaiser's yards operated around the clock, 3 shifts covering every hour of every day, with welding sparks visible from San Francisco 20 miles away. The shipyards became cities unto themselves, complete with medical facilities, child care centers, and housing developments constructed as rapidly as the ships themselves. Workers who had never earned more than subsistence wages found themselves with steady paychecks, and employer-provided healthcare through Kaiser's revolutionary prepaid medical program. The human element of Kaiser's achievement proved as remarkable as the technical innovations. Women comprised nearly 30% of his workforce by 1943, many working industrial jobs for the first time in their lives while their husbands served overseas. African Americans found skilled positions, previously barred by union discrimination, their welding certifications carrying the same authority as any workers. Wounded veterans discovered that missing limbs didn't prevent them from operating cranes or managing prefabrication schedules. The shipyards became accidental laboratories of American equality, where performance mattered more than prejudice and capability counted more than convention. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Kaiser's competitive advantage extended far beyond speed to cost efficiency that revolutionized maritime economics. His ships were completed in 2/3 the time at 1/4 the cost of traditional shipyards, margins that made conventional construction methods obsolete. The secret lay in standardization and mass production techniques borrowed from automotive manufacturing. Identical components produced simultaneously across the continent, then assembled with mathematical precision at final construction sites. Labor costs plummeted when workers mastered single tasks rather than comprehensive maritime skills. Material waste disappeared when every plate and beam was cut to exact specifications before reaching the shipyard. The economic transformation was as profound as the technical revolution. The catchphrase of the era, "Build ships quicker than the Japanese can sink them," captured both the urgency and the audacity of Kaiser's mission. German U-boats were destroying Allied merchant vessels faster than traditional yards could replace them, creating a race between American industrial capacity and Axis naval power. Each day's delay meant additional cargo ships resting on ocean floors, their crews dead, their supplies feeding fish instead of Allied armies. Kaiser's assembly lines represented America's industrial immune system, generating replacements faster than enemies could destroy them. The mathematics were simple but stark: produce or perish. The celebration surrounding each launch masked the enormous technical risks Kaiser was accepting with every welded hull. No one had tested Liberty ship construction techniques in North Atlantic storms. The continuous welded seams that enabled rapid assembly created potential failure points unknown in riveted construction. Steel chemistry optimized for mechanical joining might behave unpredictably when fused at welding temperatures. Kaiser was conducting the largest metallurgical experiment in maritime history, using vessels that would carry American lives through submarine-infested waters. Every launch represented a bet that American industrial innovation could overcome centuries of maritime tradition. Production efficiency reached levels that seemed to violate physical laws. By late 1943, Kaiser's yards were launching completed vessels faster than some traditional facilities could install engines. The Joseph N. Teal's 10-day construction time meant that every component from massive propeller shafts to tiny electrical fittings had been manufactured, transported, and installed with precision approaching perfection. Any delay, any misfit, any quality problem would have extended construction time. The achievement required coordination between hundreds of suppliers across the continent, each delivering components that had to mate perfectly with parts manufactured thousands of miles away. The impossible had become routine at Kaiser's shipyards, where daily launches created a rhythm of industrial achievement that redefined American manufacturing capability. Workers arrived each morning knowing they would complete tasks that had been considered impossible just months earlier. Welders fused seams with precision that exceeded traditional riveting. Crane operators positioned 250-ton sections with tolerances measured in inches. The assembly lines hummed with the confidence of people who had discovered they could accomplish anything when survival demanded excellence. Kaiser hadn't just revolutionized shipbuilding. He had proven that American industrial capacity could expand to meet any challenge when necessity eliminated the luxury of conventional thinking. But winter 1943 would bring a reckoning that threatened to destroy everything Kaiser had built. The radio message from the SS John P. Gaines reached Coast Guard headquarters at 3:17 a.m. on November 14, 1943. The transmission was brief and chilling. Ship breaking apart, hull fracturing amidships, 10 souls lost, abandoning vessel. Within hours, similar distress calls crackled across Atlantic shipping lanes as Liberty ships began suffering catastrophic structural failures that defied every principle of naval architecture. The SS Schenectady provided the most horrifying example, a crack racing down both sides of the hull to the keel with explosive speed. The ship's midsection turning skyward, while bow and stern sections plunged deeper into frigid North Atlantic waters. The welded seams that had enabled Kaiser's production miracle were splitting apart, and men were dying in freezing seas thousands of miles from home. The scope of the crisis became apparent as reports flooded into Washington throughout the brutal winter of 1943 and 44. Over 1,000 ships developed cracks ranging from minor surface fractures to complete structural failure. 190 vessels sustained serious fractures that compromised their seaworthiness. A dozen broke completely in two, their crews facing the choice between lifeboats in freezing seas or riding hull sections to the ocean floor. The mathematical horror was inescapable. Serious casualties occurred at 4.3 incidents per 100 ship years, compared to 1 per 100 ship years for traditional riveted vessels. Kaiser's revolutionary construction methods weren't just failing. They were killing sailors with mechanical precision that seemed to validate every warning the traditional shipbuilding industry had issued. The technical investigation, launched in April 1943, revealed metallurgical nightmares hidden within Kaiser's welded hulls. Secretary of the Navy Frank Knox appointed a board to investigate design and construction methods of welded steel merchant vessels, a bureaucratic response to an engineering catastrophe that was costing the nation $50 million and irreplaceable lives. British metallurgist Constance Tipper emerged as the investigation's most crucial figure, her crystallographic expertise enabling her to read fracture surfaces like crime scenes. What she discovered challenged fundamental assumptions about steel behavior that had guided shipbuilding for centuries. The steel itself was fatally flawed, its chemistry optimized for riveted construction where mechanical joints contained crack propagation. Sulfur content was dangerously high while manganese remained inadequately low, creating internal weaknesses that became catastrophic when exposed to welding temperatures exceeding 2,000 degrees Fahrenheit. The molecular structure that performed adequately when plates were mechanically fastened became brittle and unpredictable when metallurgically fused. Kaiser's welders, trained in 10 days rather than traditional 6-month apprenticeships, created defects during seam formation. Microscopic imperfections that became fracture initiation points under stress. The welded hulls that enabled rapid construction also created continuous failure paths where cracks could race unimpeded from bow to stern. The most insidious enemy proved to be temperature itself. North Atlantic waters transformed steel from ductile metal into glass-like material through a phenomenon called ductile to brittle transition. Steel that bent under stress in warm conditions shattered explosively when cooled below. Critical temperatures. Traditional riveted construction had masked this behavior for centuries because cracks stopped at joints between overlapping plates. Welded hulls eliminated those natural crack arresters, creating continuous metal surfaces where fractures propagated with unstoppable momentum. Square hatch corners, designed for manufacturing convenience, became stress concentrators that initiated failures, while inadequate understanding of fatigue loading meant ships were breaking apart under stresses their designers never anticipated. The human cost mounted throughout the winter as more vessels succumbed to structural failures that seemed to follow no predictable pattern. Ships broke apart while riding at anchor in calm seas. Others survived North Atlantic storms only to fracture while loading cargo in protected harbours. The SS Pendleton split completely in half off Cape Cod, requiring one of the most dangerous Coast Guard rescues in maritime history. Crews began reporting ominous creaking sounds from hulls under stress, the steel itself crying warnings that welded construction had revealed flaws hidden for millennia. Insurance companies started refusing coverage for welded vessels, while merchant sailors demanded hazard pay for serving aboard ships they considered floating death traps. Kaiser faced the professional and personal crisis that threatened to destroy his reputation and vindicate every traditional shipbuilder who had warned against his revolutionary methods. The man who had built Hoover Dam and revolutionized American construction found himself accused of murdering sailors through reckless experimentation with unproven techniques. Maritime unions demanded immediate cessation of welded ship construction. Navy officials who had reluctantly accepted Kaiser's production methods now questioned whether speed was worth the cost in human lives. The industrial miracle that had enabled America to replace sunken vessels faster than enemies could destroy them was killing more sailors than German torpedoes in some Atlantic sectors. The technical truth emerged slowly, as metallurgists like Constance Tipper dissected failed hulls with scientific precision that bordered on forensic investigation. The problem wasn't welding itself, but the interaction between flawed steel chemistry, inadequate quality control, and environmental conditions that traditional construction had never confronted directly. Inexperienced welders created internal defects during seam formation. Poor steel composition made hulls brittle at low temperatures. Square corners concentrated stresses beyond material limits. The failures represented a perfect storm of metallurgical ignorance, masked by construction speed that left no time for comprehensive testing or quality improvement. The winter of 1943 became a crucible that tested whether American industrial innovation could overcome its own hubris. Each structural failure provided additional data about steel behavior under conditions that peacetime construction had never encountered. Naval architects began understanding that welded construction required fundamentally different approaches to materials science, quality control, and structural design. The ships breaking apart in Atlantic storms were inadvertently conducting the largest metallurgical experiment in maritime history, their failures teaching lessons that would revolutionize materials engineering for generations. Kaiser's revolutionary construction methods hadn't caused the steel chemistry problems that led to catastrophic failures. They had simply exposed flaws that riveted construction had hidden for centuries. The welding process revealed brittleness that had always existed, but had been contained by mechanical joints that arrested crack propagation. The crisis represented not the failure of innovation, but the painful discovery that traditional materials were inadequate for modern construction techniques. American shipbuilding was learning the most expensive lesson in industrial history. Revolutionary manufacturing methods demanded equally revolutionary understanding of material science, and the education was being paid for in human lives scattered across the floor of the North Atlantic. The final report from the board to investigate design and methods of construction of welded steel merchant vessels arrived at the Navy Department in January 1946, its conclusions vindicating Henry Kaiser in ways that transformed national understanding of both metallurgy and industrial innovation. 970 of 4,694 welded merchant ships had sustained fractures during wartime service, a sobering statistic that nonetheless represented the survival of over 3,700 vessels that had carried the supplies, enabling Allied victory. The board's most significant finding challenged every assumption about Kaiser's responsibility for the SOPAR failures. Welded construction hadn't caused the problem, but had exposed fundamental flaws in ship steel chemistry that riveted construction had masked for centuries. Constance Tipper's metallurgical analysis provided the scientific foundation for Kaiser's vindication. Her crystallographic expertise revealing that steel composition itself was the true culprit. The material used in both welded and riveted ships contained sulfur levels that were dangerously high and manganese content that was inadequately low, creating internal weaknesses that became catastrophic under stress. Riveted construction had hidden these flaws because mechanical joints acted as crack arresters. Fractures stopped at boundaries between overlapping plates rather than propagating through continuous metal. Welded hulls eliminated those natural barriers, creating continuous failure paths that exposed the brittleness that had always existed but had never been tested at scale. Kaiser's revolution in construction methods had inadvertently conducted the largest metallurgical experiment in maritime history. The engineering solutions implemented during 1944 proved that American industrial capacity could adapt and overcome even the most catastrophic technical failures. Naval architects redesigned Liberty ship construction to include riveted crack arrestor seams at critical stress points, combining the speed advantages of welding with the failure containment benefits of mechanical joints. All corners on windows, doors, and hatches were rounded to eliminate stress concentrations that had initiated many fractures. Victory ships, the successor design, incorporated these lessons from the beginning, featuring less rigid hull designs better able to handle fatigue loading and thermal stress. The improvements were implemented with characteristic American speed. New construction standards appeared within months of identifying the problems. Quality control measures instituted after the winter crisis of 1943 transformed welded ship construction from experimental technique to reliable manufacturing process. Every welder underwent additional training focused on preventing the internal defects that had initiated many failures. Inspection became mandatory for critical seams, revealing flaws invisible to surface examination. Steel chemistry standards were revised to ensure adequate manganese content and reduced sulfur levels. Welding procedures were standardized across all yards, eliminating the variations that had created inconsistent seam quality. The systematic approach represented industrial learning accelerated by wartime necessity, compressed into months what would normally require years of peacetime development. The statistical vindication of Kaiser's methods became undeniable, as the war's end enabled comprehensive analysis of Liberty ship performance. Of 2,710 Liberty ships built, only 200 were lost to enemy action, a survival rate that testified to both their structural adequacy and their strategic importance in winning the war. The vast majority served faithfully throughout the conflict, carrying millions of tons of supplies across submarine-infested oceans. Many continued operating for decades after the war, their welded hulls proving as durable as traditional riveted construction once steel chemistry problems were corrected. The minor design changes and rigid welding controls implemented in 1947 eliminated Liberty ship structural failures until 1955, when the last vessels were finally retired from service. The technological legacy of Liberty ship failures extended far beyond maritime engineering to revolutionize understanding of material science and structural design. The systematic study of crack formation and propagation initiated by the crisis evolved into the discipline of fracture mechanics, fundamentally changing how engineers approached structural analysis across all industries. Steel manufacturers developed alloys with vastly improved resistance to brittle fracture, incorporating lessons learned from analyzing hundreds of failed ship hulls. The welding techniques perfected under wartime pressure became standard practice in construction, shipbuilding, and manufacturing industries worldwide. Kaiser's revolutionary methods, refined by painful experience, laid the foundation for modern industrial production techniques. The international impact of Kaiser's innovations became apparent in the decades following the war, as former enemies adopted and perfected his mass production methods. Japanese and South Korean shipbuilders studied Liberty ship construction techniques, incorporating modular assembly and welded construction into shipyard designs that would eventually dominate global maritime manufacturing. The lessons learned from American structural failures enabled these industries to avoid similar problems while achieving production efficiencies that surpassed even Kaiser's wartime achievements. The knowledge gained at such terrible cost during the North Atlantic crisis became the foundation for post-war industrial supremacy that shifted from America to Asia. Kaiser's human legacy proved as enduring as his technical innovations. The healthcare system born in his shipyards continued to serve millions of Americans decades after the last Liberty ship slid down the ways. Kaiser Permanente, originally created to provide medical care for shipyard workers, evolved into one of the nation's largest healthcare organizations. The prepaid medical coverage that had been revolutionary during wartime became a model for employer-provided health insurance that defined American benefit systems for generations. The integration of medical care with industrial employment that Kaiser pioneered in Richmond shipyards influenced national discussions about healthcare access and delivery that continued well into the 21st century. The final vindication of Kaiser's vision came not from technical analysis or statistical studies, but from recognition that his methods, however dangerous they seemed to traditional experts, had been the only way to achieve the impossible. Traditional shipbuilding techniques, however safe and time-tested, could not have produced vessels fast enough to replace those being sunk by German submarines. At conventional construction rates, Britain would have starved before American industrial capacity could supply the merchant marine necessary for Allied victory. Kaiser's willingness to accept unknown risks with welded construction enabled America to build ships faster than enemies could sink them, transforming industrial capability into strategic advantage that helped win the war. The steel plate being lifted by cranes at Richmond Shipyard No. 3 in the final days of the war represented both ending and beginning. The keel plate for what would be among the last, Liberty ships, positioned as the previous vessel touched water for her maiden voyage. The production line that had seemed impossible in 1941 had become routine by 1945, its rhythm as steady as American industrial heartbeat. Kaiser had taught his nation that sometimes the most dangerous path forward was the only route to survival, and that American innovation could overcome any technical challenge when necessity eliminated the luxury of conventional thinking. The legacy extended far beyond the 2,710 Liberty ships and 531 Victory ships that Kaiser's revolution helped produce. Women who had welded hull seams returned to homes carrying confidence that they could perform any task society claimed was beyond their capability. African Americans who had operated precision equipment demanded equality in civilian employment that wartime necessity had temporarily granted. Wounded veterans proved that disability was a social construct rather than an immutable limitation. The shipyards had demonstrated that American industrial capacity, when properly organized and motivated, could accomplish feats that traditional wisdom declared impossible. By 1944, American shipyards were producing merchant vessels at rates that exceeded the wildest projections made just 3 years earlier. 3 Liberty ships launched daily, 21 ships per week, 90 merchant vessels monthly. The production numbers that would have seemed like science fiction in 1941 had become statistical reality by the war's midpoint. Kaiser's 7 shipyards alone produced 1,490 vessels during the war years, 27% of all maritime commission contracts. The 4 Richmond shipyards built 747 ships, more than any other shipbuilding complex in the United States. These weren't crude wartime expedients, hastily assembled and quickly forgotten. They were sophisticated cargo vessels that served for decades, their welded hulls proving the validity of Kaiser's revolutionary vision once metallurgical problems were understood and corrected. The SS John W. Brown and SS Jeremiah O'Brien remain operational today, floating museums that testify to the durability of properly constructed welded ships. The mathematical vindication was undeniable. Kaiser's shipyards built Liberty ships in an average of 42 days by 1943, compared to 230 days using traditional methods. His construction costs ran 1/4 of conventional shipbuilding expenses. His workforce achieved productivity levels that exceeded peacetime standards by factors that traditional experts had declared mathematically impossible. The revolution that began with welding torches in Richmond shipyards transformed how America thought about manufacturing, capability, and the relationship between innovation and risk. Sometimes the safest path forward is the most dangerous one to travel. Sometimes conventional wisdom is simply conventional, lacking the wisdom that comes from confronting impossible challenges with fresh eyes. Kaiser had proven that American industrial genius, when unleashed by necessity and unbound by tradition, could rewrite the fundamental rules of what manufacturing could achieve. The lessons learned in those frantic years between 1941 and 1945 would echo through American industry for generations. Mass production techniques refined on Liberty ships would revolutionize post-war consumer goods manufacturing. Quality control systems developed to prevent welding defects would become standard practice across all industries. The systematic training methods that transformed inexperienced workers into skilled welders in 10 days would inspire vocational education programs nationwide. Most importantly, the demonstration that ordinary Americans could quickly learn to perform extraordinary tasks would challenge class assumptions about capability and potential that had constrained social mobility for generations. The impossible had become inevitable, one welded seam at a time. From Richmond's muddy shipyards to the floor of the North Atlantic, from Constance Tipper's crystallographic analysis to the final statistical vindication, Kaiser's revolution had transformed not just shipbuilding, but America's understanding of what industrial democracy could achieve when survival demanded excellence and urgency, eliminated the luxury of discrimination. The welding torches that burned in Richmond, Portland, and Vancouver during those desperate war years did more than fuse steel plates. They welded together a new vision of American capability, proving that innovation matters more than tradition when civilization itself hangs in the balance. Kaiser's legacy lived on in every modern manufacturing facility that employed assembly line techniques, in every welded structure that bore loads, once thought impossible, in every training program that transformed novices into skilled workers in weeks rather than years. The 7 shipyards that revolutionized maritime construction during World War II had closed by 1946, their massive cranes silent, their welding stations cold. But the principles they had proven, the methods they had perfected, the assumptions they had shattered, these lived on. In the post-war economic boom that made America the world's industrial powerhouse, in the civil rights movement that demanded equality proven possible in wartime shipyards, in the modern manufacturing techniques that traced their intellectual DNA directly to those frantic years when America built ships faster than enemies could sink them, Kaiser had set out to solve a simple problem: build enough cargo ships to win a war. What he created instead was a revolution in human capability, a demonstration that properly organized and motivated, ordinary people could achieve extraordinary results when given the opportunity and training. The Liberty ships that survived the war went on to carry cargo across peaceful oceans for decades, their welded hulls vindicated by time and statistical analysis. But their true legacy wasn't measured in tons of cargo carried or miles sailed. It was measured in the changed understanding of what American industrial capacity could achieve when necessity met innovation and traditional wisdom met revolutionary thinking. November 16th, 1942. 71 hours and 40 minutes from Keel laying to launch. The impossible made routine, the dangerous made safe through understanding, the revolutionary made standard through systematic improvement. Kaiser's vision transformed American manufacturing and helped win the war. But more importantly, it proved that the most unsafe path forward was sometimes the only way to survive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.